So last day, Quinn, we looked at orbits, and here was our theory. We basically said, first of all, if you're moving in orbit, the key idea is that gravity is what's pulling you in a circle. That's my starting point. And then, depending on what they ask for or what they give me, I'll modify my next few lines. But we started saying there's a bunch of equations that jump out of here. We did say, Jordan, that people think that in orbit, the astronauts are floating because there's no gravity. That is incorrect. In orbit, there is gravity. The gravity up there is the same as the gravitational field strength, Mac, which is the same as gravity in free fall. And in fact, the reason the astronauts look like they're floating, the reason the astronauts are floating, is not because there's no gravity up there, it's because they're in free fall. But what we said is they're in free fall with just the right horizontal or centripetal velocity, circular speed, so that as they fall, they're moving sideways, and even though they're falling towards the planet, they miss the planet every time. They keep missing the planet. So we said, okay, as far as I'm concerned, there's three big concepts. There's your orbital speed, which I called V-orb. There's your orbital radius. And there's your orbital period, how long it takes to go around. If I give you any one of those, you can find the other two. Then there's another thing related, called orbital altitude, which really is find the orbital radius, and then if you want how high you are above the planet, subtract the radius of the planet. So we looked at right here, we had changed example 5. Leonard, if you want to, instead of 300 minutes, we'd said, oh, got to make it seconds. And then it wanted the altitude. And we got to what is the satellite's orbital velocity? Really, I should say orbital speed, because the velocity, what direction? I guess tangent to the radius. But you know what? I would say this. Gravity is what's pulling me in a circle. Devin, what did we find in part A? We found the altitude, and in order to find the altitude, what else did we have to find? The radius, and I know the period. I could go like this. I could go circular speed equals 2 pi r over the period. We'll quickly try that on our calculator later on, and hopefully we get the same answer both ways, and then we'll know part A was probably right. But for now, I'm going to say big G, big M, little m over r squared equals, I guess, mv squared over r, because they want the orbital velocity. Oh. Turns out the mass cancels once you're up there. It doesn't cancel to get up there. It's more fuel to get heavier objects up there. But to keep them up there, Riley, is piece of cake. And do these R's cancel? One of them does. Because this R would move to the top, stuff moves diagonally. Careful, remember for this situation, the R's didn't cancel. In fact, we ended up with an R cubed and had to cube root. So don't always assume the R's cancel. That's a common mistake. Oh, what R always cancel? No, depends on the equation. Okay, so we get (6.67 times 10 to the negative 11). 5.98 times 10 to the 24th, all over R. 1.48 times 10 to the 7th. Now, if I was, Tice, doing these questions back to back, I probably would still have my answer button, my R, because to 3 sig figs, we're going to be off by a little bit. I would love to be a bit more accurate, but whatever. We had a day break here, so it is what it is. Again, It bears repeating. It's worth practicing on your calculator like crazy during these lessons because, by the way, it's going to get tougher, more calculator stuff today. Today and tomorrow, next lesson, you may recall when we did momentum, I told you guys that was the second longest question you would do all year. This will be the longest one today, which is how much work it takes to put something in orbit. Yay! I can hardly wait, Mr. Duick. Yeah. And then square root of that. And I get 5.19 times 10 to the third, 5,190 meters per second. Okay. Nice yawn. I could check using this method by going 2 pi times r over the period. What was the period? 18,000? Was it? Yeah? A little off. Close. I could also check. The other thing I could have done is I could have said, well, since they gave me the period, don't write this down, I'll just walk you through it. I could have said the circular accelerations have to be the same for both of them. I could have said 4 pi squared r over t squared has to equal v squared over r. I don't think there's any way that I can get there without using the r that I found in part A. Jordan, rather than memorizing a bunch of approaches, my fallback is almost always, hey, am I in orbit? You know what I know? Gravity is what's pulling me in a circle. Also, I've played around with all the other approaches, Isaac. They're not significantly shorter enough to make it worth me memorizing yet another procedure. It's kind of whatever. I got something that works. I got a one-size-fits-all. Speaking of one-size-fits-all, oh, I guess I said if you wanted to, we could write here r equals the cube root of, what was it? Big G, big M, t squared over 4 pi squared. Again, Isaac, don't memorize it. Big G, big M, t squared over 4 pi squared. I mean, you can memorize an equation like that, but Riley, it all comes from gravity is what's pulling me in a circle, and then we cross multiply. 1 fraction equals 1 fraction. Stuff moves diagonally with a vengeance. And it's really this equation here that already in Physics 11 I had in mind when I start pushing the formula manipulation. Because to try and plug in numbers, Colin, and just solve that by hand, because I think initially at the beginning of last year you were still liking to plug in numbers, it can be done, but I've sold you on the formula manipulation approach and no triangles, right? Say yes. We already watched the Japanese astronaut playing baseball. We watched Chris Hadfield. What is gravity? This is a complicated question. Gravity is a weird force because unlike this force where I'm actually coming in contact with Tamara, I'm pushing on her and she feels a force. The problem, Kate, is gravity can act on you. I can exert a force of gravity on you from a distance without touching. Sir Isaac Newton actually said, look, the equation that I've given you calculates gravity, big G, big M, little m over r squared, but I have no idea what it is. I don't know what gravity is. So Sir Isaac Newton gave us the equation. Einstein came along and he suggested that gravity in general relativity could be imagined like a warping of space and time. So put your pencils down. Here is the analogy we have. Not on the test, but just nerdy. I like example 6, I like example 6, I like example 6. It says this, a satellite has an orbital altitude of 1.2 times 10 to the 6 meters above the Earth. A says, what's its orbital radius? Okay. When it says the altitude, I think what it's told me is that distance there, above the surface. How could I figure out the orbital radius, our orb? how could I figure out... That's silly, Mr. Dewick. How could I figure out that distance? Yeah, at the radius of the Earth. And what I'm really saying is, Devin, just read the questions carefully. Sometimes they'll give you the orbital radius. Oh, great. Sometimes they'll give you the altitude. Sometimes they'll ask for the orbital radius. Oh, great. Sometimes they'll ask for the altitude. Okay, I got better do a little bit more math when I'm done. But you want to do all of your calculations with the orbital radius. So the orbital radius is going to be, I'll write in our notes, our Earth plus altitude, which is going to be 6.38 times 10 to the 6th. I'm going from memory, but I think I saw Lewis looking it up. Yeah? Okay. And the altitude is 1.2 times 10 to the 6th. Hey, are they both times 10 to the 6s? You know what? It's going to be 6.38 plus 1.2. It's going to be 7. Double check me, but I'm pretty sure it's going to be 7.58 times 10 to the 6th. Yes? Okay, meters. Don't forget units, since they actually asked me that. There. And here's what I've said. Jake, if I give you any of the orbital radius or the orbital period or the orbital velocity, you can find the other two. Here we've got the radius. I bet you in part B and C they're going to ask me to find the other two. What do they want me to find in part B, Jake, my friend? Oh. And I need to go through and change these all to speed, because velocity should have a directional component. I guess the direction is always perpendicular to the radius, tangent to the radius, but okay. How am I going to start? Gravity is what's pulling me in a circle. You know what? How about, did I leave you guys lots of room? I did. I'm going to do... I'll do B all the way down on the left, and I'll do C all the way down on the right. That works. Then you can kind of see line by line how they compare to each other. It's going to be big G, big M, little m over R squared equals M. Don't forget the M. Well, don't write this down. I want circular acceleration. Which version of circular acceleration do I want to put here? Oh, because they said speed or velocity? Okay. Yay! Did I also give you guys a take-home quiz for homework? One that we need to be marking? Brain just clued in on that, too. We'll do it in a second. Does an R cancel this time? This time one does, and I usually just go like that. And we get, I think we've seen this equation before, big G, big M over R. Double check, are we Earth? Always check the planet. Sometimes just for giggles and dreams, I'll put you on the moon, then use the mass of the moon, which is on your sheet. Sometimes just for fun, I'll have you orbit the sun, or I'll make up a planet. I'm fond of making up planet Dewick, which for some reason often has a radius that's a multiple of pi and a mass that's a multiple of e, because if I was designing a planet, that's what anyways, if you notice those nerdy things. Plug and chug. 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th. And Leonard, all these values are on our formula sheet, on our yellow or blue one. And it's the orbital radius, which was 7.58 times 10 to the 6th. Looks right. Square root of that. I think last day we said if you wanted to orbit right at the Earth, it was like 8,000 meters per second, a little more than that. So as you move further out, you don't have to move as fast to stay up there. So you'll usually get answers in the 7,000, 6,000, 5,000, 4,000 range. If you get an answer bigger than 8,000, you've made a mistake. Am I right? 7.25? Times 10 to the 3 meters per second. $7.254. C. Orbital period. I probably could find the orbital period. Now that I know the orbital speed, I could go v squared over r is going to be equal to 4 pi squared r over t squared, because the accelerations have to be the same, and that's one way. You know what? I still tend to fall back on, hey, gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals m. I guess now I'm going to use the 4 pi squared r over t squared. Get the t by itself. Do the r's cancel this time? No, I'm going to get an r cubed, but I don't have to cube root because I'm not trying to get the r by itself. I think what I'm going to end up doing is moving the t squared there, the r squared there, and these guys to the bottom. Is that right? Stuff moves diagonally? I think I'm going to get this. T squared equals 4 pi squared r cubed over big G, big M. That's t squared. Colin, I'd be curious to see what a triangle would look like, or I'd be curious what shape would end up appearing for something like this, I think. Plug and chug, complicated plug and chug. Again, really encourage you, practice on your calculators. 4 pi squared r was 7.58 times 10 to the 6th cubed all over 6.67 times 10 to the negative 11 times 10 to the 24th. Four pi squared 7.58 times 10 to the 6th cubed. I don't think I need to put my calculator, I think, knows if I cube it, it cubes the whole thing. You might need to put that in brackets on yours. Divided by, definitely got to put the bottom in brackets because there's more than one thing on the bottom. Sheesh. Square root answer. Is that right? 65, 65, 5? Yeah? I guess 6.57 times 10 to the 3rd. And that's a period, so it's seconds. No? Yeah? Or if you want to, divide by 60. About 109 minutes. Goes around the Earth every 109.4 minutes. Okay. What if you wanted it to take longer? Would you want the satellite to be up higher or up lower? Higher. And with that cubed on the R, it's actually a very, like even if you go a tiny bit higher, oh yeah, it's actually, you've added to the period quite a bit. Go a tiny bit higher, you've added to the period quite a bit, because now there's a cubed. So twice as high would be 8 times longer. Okay? 2 cubed. The geosynchronous satellites, the ones that stay above the same place on the Earth, what would their period be if they stay above the same place on the Earth? 24 hours. Those all have the same height. You can, in the homework, I actually ask you to crunch it, and you'll say, oh, those are way out there. And they are. They're pricey because you got to give it all the fuel to get it that high. Because remember, getting it up that high means it's gaining potential energy. Where does that energy come from? Fuel. Right? So I already assigned 1, 2, 3, 4, sorry, 1, 3, 4, 5, 6, 7. Nine is good. Ten is good but tricky. And then if you just want lots of practice with this, 12, 13, 14. Basically, in number 12, I gave you V, and I said if I give you V, you can find the other two. In number 13, I gave you the altitude, which you can use to find the radius, which then you can find the other two. And number 14, I gave you the period in hours. You'll have to do a conversion to change it to seconds, and you can find the other two. Okay? Could you get out the take-home